My name is Blum, and I'm a big data architect for Verint systems. I will tell you about our application of data science in our cyber defense system. This is a sneak preview of a talk that I'm going to give in 2 weeks from now at the Strata Data Conference in London. So I hope, this is half the time, so it's half the content. So let's see how we can take the major points out of it. So a bit about myself. I'm a big data architect, as I said. Been working with big data, I can say, for 15 years, but it wasn't really big data then. We didn't call it that way, but data fusion algorithms or data tiering in databases. But I've been around that subject for a while, and I've been for about 5.5 years in Verint. And this system that I'm going to talk to you about is a system that we had a major shift in its functionality. It's been a collection-based system, which is something that our system has been doing for like 20 years. And it shifted now to be an analytic system. And it really changed the whole operation of it, of course. So, we had a couple of cyber talks now, and it also was about APTs, so I'm not going to start again about it, but like in a nutshell, it's about countries attacking countries. It's like a nation-level attacks. These are attacks that are very long. They have a low footprint, and they exploit like very unknown exploits in the systems. Okay, so their fingerprint is very low and hard to detect. So these are just, you can Google, and every once in a while you have these, one country attacked another, and and as we heard before, there's not a lot of data actually out there. So it's also a very big challenge in that aspect. So I don't know. I know we had two cyber talks now, but like a quick show of hands, how many of you are like working with cyber, no cyber? Like, okay. So I think I'm not going to skip this one, unless you're shy, I know. So I'm going to really fast because time is short. This is a presentation for people that don't know anything about cyber, okay? So anything. So I'm going to start with a very basic, what kind of data we have when we analyze a cyber attack. So let's start with the network itself. Let's look at some corporate network. We have the internet, and then some firewall, and then we have a demilitarized zone. And in that, you have all the outbound services that the corporation has, so web server, emails, etc., etc. And behind that, another firewall, and then you have the actual corporate network, which is the stuff that you really don't want. I mean, you don't want people to mess around with that, but you really don't want people to mess around with that. And when you enter that, you have everything that you would expect to have, databases and client endpoints, and user management, etc. And like, let's think of one very basic attack scenario. We have a malicious agent over there. He's on the internet somewhere. We don't know where. And here starts something that is called the cyber kill chain. So we're going to breeze through it. Just at first, he would define its goals. He would look and see where can I attack, what I wish to gain from this attack. And then we'll gather intelligence. It can be from various sources. It can be human intelligence. It could be cyber intelligence. But eventually, after you have the targets and you have the intelligence, this agent would like to infiltrate. So first, there will be specialized tools and maybe a set of tools that are used for this attack. And then the actual infiltration. So let's start with a very simple thing. He sends an email with a gorgeous picture that you just had to click, or a link or whatever, and someone took the bait, and this agent got in. Now let's say it was some person in the network, and now he's inside, and okay, so I reached some, I don't know, guy or girl's computer whatever, but I want to get some other stuff. So I would have a call home phase. I have like a command and control server or a group of servers out there that I would contact. I would send some packets and say, I'm over here, tell me what to do. And then you would get an order to move laterally inside the organization. Then the lateral movement phase got me to a database. And once I'm there, it's the data exfiltration, game over. I sent everything out. OK, so this was a very, very basic scenario. What happens after all of this, when the chain is complete, we say, OK, what can we do about it? So what would you do? You would deploy sensors, OK, all around. And I'm not going to get into the time that I have on all of these, because each one of these is like a week workshop. But the idea is that these sensors cover different parts of the cyber kill chain. And the more sensors I have, the more of the chain I cover. But what do I do with all of this? I mean, this information is very noisy. Each of these sensors is very noisy. Now imagine like you have a very imbalanced situation. You have like a very, very low false positive rate. You have 0 false negative, a very low false positive rate. But these attacks have such a low footprint that the false positives outweigh per sensor the actual attacks. So what happens is you have alert fatigue. You have to scan like 100 alerts to get one true case. So the whole issue about it, the whole analysis is how to correlate all that information and create an actual picture and understand that there was an attack. So just to make the image a bit more complex, usually it's not one organization. There are a few organizations, and the system backhauls all the information, sits at a service provider that provides this cyber defense service. So let's look at the system. I mean, I know this is like very data science conference, and it's great, but we have to remember that this system serves not only data scientists, and we have to put on the same system the same capabilities for data scientists, but also for the usual operation of a cybersecurity operation. So you have a cybersecurity operator that it works with the system like a information management system. He sees all the alerts and can browse through them, and he expects like a very quick operation. Then you have like a cyber analyst. This guy would like to have more in-depth look, like when the operator sends like suspicious stuff to him, he would really analyze like more in depth and say, okay, maybe there was a real incident here. Then you have the data scientist. When these guys are blocked, they will ask her to really understand if there was something new that the system didn't find so far. And of course, and I'm gonna breeze through that, but we have DevOps and managers that want to have everything in a very low footprint and in a single cluster and all these technical things that make our life simpler. But the idea is that eventually this system has to serve both interactive actions in seconds and also minutes if we'd like. But on the other hand, it can work all night training a model for the 10 hours, and all in a very low footprint in a unified cluster. And well, I'm not going to get into sizing. This is an example of like 100 gigabits network, but eventually it's hundreds of thousands of events per second, and the retention is of a few months, and it gets to trillions of events and petabytes of information. So these are all our constraints, and how we went on and solved that. So I don't know, how many of you are familiar with the whole democratization of big data, Hadoop? I'm sorry for that question, but is anyone here unfamiliar with that? Or okay, let's do it positive. Everyone that is familiar, raise your hands. Maybe it will reach us now. Oh yeah, okay, great. So, but still some didn't raise, so I'll explain even better. So what we did here is the whole system that was composed of various silos of information. We made this unification process. And it really gained momentum in the last couple of years when this frameworks went really, really stable and production ready. So the Hadoop ecosystem for mostly HDFS, the file system for storing all the information, and Spark is our major processing framework, both processing and Spark ML for machine learning, and we have Hadoop Yarn for scheduling, Ambari to manage the cluster, and Airflow to manage our jobs. I will give more examples soon. And Elasticsearch is for result set exploration. Kafka is our backbone of messaging in the system, in the Avro serialization over it. In the Hadoop, we keep all that information. So it's mostly Parquet files, but we have CSVs and binary pickups. I mean, it depends on the deployment, but some deployments keep for a certain amount of time the actual raw traffic for further analysis. All of that by a centralized DevOps operation. And on top of that, we have like 5 teams that write actual applications on top of this framework. So it starts from basic streaming, enrichments, and correlations. Some correlations are more complex and some are more simple. Some are statistical correlations and some are more validated by IDs that we have in the network. We keep all the information in a large-scale repository on top of this framework. We have entity analytics, what it's also, like profiling of the entities in the system. We'll talk about that soon. Between these entities, we also had graph analytics and algorithms on top of them. A rule engine to trigger rules in real time for events that may happen, predefined the events that we wish to trigger. And also we have a whole group of machine learning detection of events on encrypted traffic. So all of that is also available for data exploration because of this open framework, which really makes our life easier when we're talking about our research to production phase, which I will talk soon. And yeah, that's another one. OK, so I'm going to talk about a bit about entity analytics and then about our research to production cycle. So this is one example of our application, what we do when we want to understand what are the entities in our network. We aggregate streaming every 15 minutes. And then we have batch jobs that aggregate hourly and daily and weekly and monthly. And we have day of week and day of month and month of year. And we, for each of these, if we look at the knowledge layers that we create from these first aggregations and then further analysis, we look at like a host or a URL or a user in a network. And on top of that, we have a simple aggregation. How much traffic, what applications did he use, etc. Then we recognize patterns. Once we have these patterns, we can understand the characteristics of this entity. For instance, if it's a user and we know which applications he uses, then we can understand that this is a sysadmin. And then we have anomalies and we say, OK, he logged in to, I don't know, an irregular endpoint or did something that was like irregular protocol, surf out of hours, etc. And these also are ways to generate alerts. So this is part of the system. This is not like a free play. This is a process that we develop and is available for the operator and most importantly for the people that for analysis, but still not for the data scientists, because data science is this is our data scientists that create this process. So I'll explain how that cycle in the next how that cycle works in the next slide. So when we talk about the big data pipeline, so just to repeat that, we have our pipe like the Kafka. Then we use Spark for stream processing. For instance, in entity analytics, it's our 15-minute aggregations. We persist everything in Parquet files. Then we batch process over the longer aggregation periods and the different aggregation types. Then, well, that's orchestrated by the Airflow. We make all the data available using the Spark Thrift server. And that is, after we have like many results, we give that results for exploration, for very rapid exploration in Elasticsearch. You can facet and aggregate only the results, so that make it much more interactive. And also, all this data is available for a data scientist. So that means that, I mean, our work, I'll explain it maybe even better in this slide. Having it all available in this framework, make it available for us to make our models, but also we have customers that want to build the models themselves. They want to explore the data themselves. So sometimes we allow that, but you understand that it's much more complex that you have like a customer free playing with your data. So you have to really limit how much processing and how much data the customer can interact with. But if we look in a very basic way how this cycle works, and I have to say that this was a very long cycle when we started this process, but it's getting faster, so we're getting better at this. First, we have an operator that works with the system and has alerts, and then he sees something that is very interesting, maybe for the analyst, maybe a group of alerts that form a real incident. Now, this analyst may see that he doesn't have all the information and say, maybe we missed something here, because we know something that for every attack that we ever seen, always you had the evidence in the logs. But there are trillions of lines, so you would miss it, and you say, okay, I've seen something here. Let's see if we can learn more about that. Then and this is mostly our data scientists, if we see that we've built something new and there is a new model that we want to maybe incorporate in a sensor that we want to have in the streaming aggregations that we have or in our probes, then that would go back to DevOps that will incorporate it in the next version, which will generate more alerts and will continue this cycle until we encounter the new one. This is not something that is like one phase. We understand and we know that this is the way it is. We know that attacks are always evolving, and we expect this cycle to go on. The main challenge is to make it as rapid as we can. So just to summarize, this is the transformation that we did that was a major part for us in the past couple of years. We couldn't have done any of data science, real data science work before we made this infrastructure change. So changing your infrastructure is a major part of actually deploying, it's very nice that we had like cool Python scripts, but having that in such a big scale, we had to make an overhaul of our product. So it's all thanks to the democratization of big data. It helped us to do a very rapid R&D. We built a team of a few dozen developers like in a very short time on this platform. It gives us very high performance, and it's very elastic. We sell very small systems, like 6 VMs, and some systems are like 200 servers, so it really varies in size. And the most important thing is the rapid research to production cycle that we always try to evolve and make it faster. That's it. Thank you.